record from your side. Right. So in the last lecture, we have seen about PET, project evaluation and review technique, right? And then we try to find out the critical path, and then we have seen how to calculate the slack time of each and every activity, right? And through setting 4 different parameters, so we have seen how you can calculate the minimum time required to finish a particular project, right? Now, so I mean, but is so using this activity network diagram, whatever we have seen as part of this PET, right? So they are not actually going to address the worst case and best case estimations, right? I mean, so here, so whatever you have seen is like the durations, whatever we have estimated, right? Let's say I told you 15, 120 for certain activities, right? Now they are the only estimates, and they are, I mean, that's, usually, whenever in real practice, so these activities will vary, right? Sometimes maybe it will take, 15 days, sometimes it will take 16 days, sometimes it may take 14 days, or sometimes it may take 13, right? So accurately we cannot say always, right? But that means that duration can vary in between, the lower bound and maybe higher bound, right? So maybe you have two different extremities of these estimations, right? So maybe, best case, I mean, best possible time it can take to finish that particular activity, maybe something. Okay, worst case time, it can take to finish that particular activity. This will be like this. Okay, in real practice, usually you will have, this duration is actually distributed, distributed over it, some sort of distributions, right? Maybe it uses, normal distribution, some sort of like this. Okay, so we'll see that. So actual duration might vary from the estimated duration, right? So utility of the activity network is very limited, because this is what exactly, as of now not addressed, right? So PET charts are more sophisticated form of activity chart, right? And in reality, that the duration of an activity is a random variable with some probability distribution. I said you, right? So now the duration of that of a particular activity can be, it is a random variable with some probability distribution. Maybe the duration will be distributed over a probability distribution, right? So maybe it is a normal distribution, like in case of effort we have seen, right? So we have seen there is a distribution, right? So usually the number of people employed at different times gradually increases, it goes to a peak and then reduces. Similarly, here also it follows some sort of probability distribution, right? So like, that particular activity, sometimes it may take 1 month, sometimes it take 10 months, sometimes it take 5 months. So you have a lot many variations. Okay. So that can be represented through some probability distribution, right? In this context, PET chart can be used to determine the probabilistic times for reaching various project milestones, including the final milestone. Now, if we can get that sort of, if you can define this, duration in probabilistic terms, then you can able to find always in probabilistic terms, you can always find, what would be the project milestone for a particular activity or for the whole project. Okay, so that is what we are going to see. So PET chart represents statistical variations in the project estimates, assuming these to be normal distribution. As I told you, so so because you do follow, you going to see there is a variations. Maybe you have some sort of statistical variations. Maybe you can see the various variance and standard deviation, these sort of things. Okay. So assuming that it follows a normal distribution. So it allows for some randomness in task completion times, therefore provides the capability to determine probability for achieving project milestones based upon the probability of completing each task along the path to that milestone. Okay, so that means you will be able to now get the duration in the milestone duration, or that means let's say the milestone here is the complete project. Okay, so I mean you can get always that completion time of that particular project in probabilistic terms. Okay. So as part of this, so each and every task is annotated with these three estimates. Okay, so one you will have is a optimistic, that means that the best possible case where the task completion time, maybe you can say in best possible case what would be the time complexity. I mean, what is the time what is the time completion time. Okay, that means in the best way maybe it takes 1 month. Okay, in the worst way it may take 1 year. Okay, most likely estimate is the average time. Okay, so average time maybe it is going to take how many months, maybe 5 months. Okay, that's this way you can think of, right? So optimistic, most likely estimate, and the worst case, right? So the optimistic and the worst case estimates, they represent the extremities of the task completion time, right? You understand, right? So it let's say there is an activity. So I have given in the previous cases example. So we have seen that there is a very crisp value, that means only 15 I said. Okay, but the duration may vary actually in practice. Okay, so sometimes it can be 13 14 or 15 or 16 or 17, it can be like this, right? So the optimistic one will be the lowest one. Okay, the worst case will be the maximum duration it takes to complete that particular task. Okay, and most likely will be the average time, right? So now the most likely estimate is the completion time that has the highest probability, because you see the average one, average estimations are actually they have the very highest probability. You can understand, right? So because I told you at time TD, so you will have a peak, right? So that means so at average time, so I mean if you plot the graph, so time versus some output, now you can see. Okay, so usually what will happen at the average, at the intermediate time. Okay, so you see the peak, right? So that means so that particular most likely estimates are the actually gives you the highest probability. Okay, that means so if somebody says like this, okay, my is a average, the most likely estimate is 5 months. Okay, and the optimistic one is what, let's say 1 month, and the worst case may be 10 months. Okay, so in that case you can tell me, if somebody will ask you giving these values, somebody will ask you, Acha, what would be the project completion time for according to you? So usually you will go with what, the average case. Why? Because sometimes you will have lower value, sometimes you have a higher value, so you always going with the average one. That means it has a more probability. That means you will be going to reach that particular time estimate, right? If you say the average value, so always there is a probability that the completion time will be fall between within the most likely estimate duration. Okay, any doubts so far, students?
No, sir.
Okay, now these three estimates, you can compute some standard deviation values by taking this, right? So let's say if you know that if you know that T0, TW, and TM. So T0 is the, and TO is the optimistic one, and TW is the worst case, and most likely is the TM, right? So now then So as I said you, so you can easily get the standard deviation, right? How you can get the standard deviation? If the value is given T0, Tm and Tw, then you can easily calculate the standard deviation, that is the STD. So STD is equal to Tw minus To divided by 6. So this is going to give you the standard deviation, right? Now, so usually, so if you say Tm plus standard deviation and Tm minus standard deviation. So can anyone tell me? So if you have a normal distribution curve, right? If follows a normal distribution, you have a mean. Okay, that means you have calculated a mean and you know the standard deviation, right? So mean plus standard deviation, mean minus standard deviation. I mean, can you tell me approximately what portion of your distribution will be covered?
67%, I think.
Yeah, I think not 60, I think less than that. Okay. If you Tm plus 2 standard deviation and Tm minus 2 standard deviation, that will
90,
probably going to give you, okay, 60 around, right? But if you go with average plus 3 standard deviation and average minus 3 standard deviation, right? So it will cover, I mean, almost 99%, I think. So the area will be covered, right? If you take Tm plus 3 standard deviations, right? So I mean, all of the samples will be taken, right? Considered, right? So that is this way, you can see entire distribution, how it lies and all, right? Now the mean estimated time, you can get a mean estimated time. So it is a average weighted time, average weighted time, right? So I mean, you can say it's a weighted average. Okay, it is a weighted average time, right? So you can get this average weighted time is something like this. Okay, so the mean estimated time, so To plus 4 Tm plus Tw by 6. Okay, that means you are giving one weight, you are giving 4 times weight, you are giving 1 time weight again to Tw. Okay, so this way you can get the average, mean, I mean, you can say average estimated time can be calculated using this equation, right? So even given this Tw, Tm, To, Tm, Tw, then you can get this estimated time using any normal distributions. Okay, so since all possible combination times between the minimum and maximum duration for every task has to be considered. Okay, so you can see, so as I told you, so the minimum time will be To, maximum time will be the Tw, right? When it is given, so what will happen? Now you can just see, now then there can be many number of many number of critical paths, you can see. Okay, why you will see many number of critical paths? Anyone tell me? Can you tell me any reason? Can anyone tell me why you will be going to see many critical paths? Okay, looking at this graph, can you tell me? So if I given something like this, okay, so my specification, okay, my specification will vary from 10 to 25. My specification will vary from 10 to 25. Okay. And similarly for 45 also, maybe something like this, 30 to 50 or 30 to maybe 60. Okay, see, if you have this sort of minimum and maximum values durations, then why you will be going to see many critical paths?
Because we'll have to consider many values from 15 also we need to 16 also we need to consider like that.
Right. So that
in
means
that range we need
if
to
you are going
consider.
to take if for every task, if you randomly pick a value, okay, between 10 to 25, what will happen? There are many possibilities, right? So from 10 to 25, any value can be picked, right? Similarly, for 45 design database also you can have many values, right? So code design also many values. Now you can have a permutation of at any point of time you can have different permutations, right? As a result, what will happen? Now for every case you will have to calculate the critical path, right? So now then there will be a many possible critical paths, okay, that may come, okay. So that is what exactly we are saying, right? So there can be many critical paths depending on the various permutations of the estimates for each task, right? So it makes critical path analysis in PERT chart very complex. If this sort of things, if you have any random values, if you are going to pick, so then what will happen? So then you will have many critical paths which will take a lot of time to analyze. So as a result, what we try to do is we going with a average estimate, okay. So the average estimate can be calculated like this: TO plus 4TM plus TW by 6. So that is going to give you average estimate, right? So once if you once if you get these values like this, okay, like TO, TM, TW for each and every task, if that is known, that is given the optimistic value as well as the worst case value, so then you can easily then you can easily calculate the average estimates, right? So that is what exactly using the equation, right? TO plus 4 times TM plus TW by 6. And then once you get the average estimates for each and every task, okay, now you can, again, you can find out what would be the critical path, okay, considering that average one, as well as you can consider, you can calculate slack time also, right? So this would be probably an average estimate of everything in terms of probability terms, right? So you'll be getting, if you following some sort of distributions usually, so you are going to get the values in this way. Clear? Any doubts so far, students? Can I move on to the other slide?
Yes, sir.
Okay. So it has been now we are into the other one. So I told you, so there are two techniques being used in the scheduling. So one is the PERT and the second one is Gantt chart. Okay. So now it has been named after its developer Henry Gantt. Okay. So he actually proposed this. So it is a form of bar chart. Okay. You understand what is a bar chart, right? So there are certain number of bars. Okay, which is going to tell you, I mean, how much percentage of something a particular bar contributes. I mean, a bar represents, right? So vertical axis lists all the tasks to be performed. Okay. So here in this case, we will see that there is a x-axis and the y-axis. So usually the y-axis called as the vertical axis here. Okay. So that vertical axis lists all the tasks to be performed. So whatever the tasks you have, for each of the tasks, you will be going to see a bar. Okay. So the bars are drawn along the y-axis, one for each task, right? So each and every task will be represented by a particular bar. Okay, so each bar consists of unshaded part and shaded part, and you will be going to see there is a shaded part as well as there is a unshaded part. Okay, so part of each and every bar, right? So now the shaded part shows the length of the time each task is estimated to take. Okay, so that means shaded part will tell you that maybe 1 month of time it is going to take. Okay, take to complete that particular uh, task. Okay, so it's all a estimate, it is a estimate. Okay, it's a estimated time, right? So unshaded part shows the slack time. Okay, so I told you, if at all any activity has any slack time, so that should be marked. So previously we have said that, right? So we have calculated that slack time. Okay, if that slack time is there, so then that will be represented by a unshaded part. Okay, so let's say a task takes 1 month of time. to finish that particular task, and 2 days may be slack time. So that means so that will be represented. So black portion, that means the shaded part will be going to say you that. So 1 month and the 2 days will be represented through this unshaded part. Okay, so the slack time represents the flexibility available in the meeting the latest time by which a task must be finished. Okay, so that means that is the flexibility given to each and every task. That is what the slack time is all about, right? So it is useful for resource planning. I mean, this Gantt chart are usually they are used in resource planning. That means how, I mean, during the allocation of resources, right? Maybe how you can allocate staff. I mean, the people who will be really working towards this particular project, right? And what sort of hardware, what sort of other softwares you really require, right? To carry out certain activities, right? So all resources can be planned if you get this Gantt chart. Okay, now we will see the same thing through the next slide. Now you can see here, right? So I told you, right? So in the y-axis or the vertical axis, so you have a task, right? And those tasks will be represented. Some portion will be shaded and some portion will be unshaded. Now you can see the design GUI part. So there you have a shaded part as well as you have unshaded part, right? As part of code GUI part, I mean, when you are going to code GUI part, so you have an unshaded part also, right? So when you are writing your user manual, so there you have a shaded part and unshaded part also, right? So unshaded part, I told you, that's a slack time. Okay, you have enough time till that particular time, right? As we have seen in case of your activity network as part of your activity network, we have seen, right? So unless or until this code database and code GUI both are finished, so you are not allowed to go into the other phase, like integrate and testing, right? Now the time is duration is written in the y-axis. Okay, so January 1st to January 15, maybe January 15 to March 15, right? March 15 to April 1st. So you have some durations, right? Now, so your bar represents how much time you are going to take this task, right? So specification is the task, so for which, so you have one bar, right? So it is going to tell you that yes, January 1 to January, before January 15 you need to finish that. Okay, so there is no slack time. Okay, maybe you will some activities, some tasks will not have any slack time, but some activities will have slack time. So in this case you do not have any slack time, but design database part also you do not have a slack time, but design GUI part you have a slack time. Okay, so slack time of 15 days, maybe March 15 to how many, April 1st, then you have a slack time of 15 days for this particular activity, right? But for design database part you do not have any slack time, right? So this way you are going to all your, now once this bar chart is prepared, now you can accordingly you can allocate the resources, right? So January 1st to January 15, between this duration you need to have whatever the tools required for analysis of your requirements, or whatever the people you need to recruit the people who are really need to going to work on this particular specification part. So all people will be, so accordingly you need to plan, right? Because you have all these things, right? So this is exactly what we can see from this Gantt chart. So it is useful in planning the utilization of resources, while compared to PERT chart, which is usually useful for monitoring the timely progress of activities. So PERT chart is only used to see the progress, timely progress, whether the activities are completed as per our deadlines or not. Okay, so but whereas Gantt chart is actually going to help you in monitoring the resources, how better way we are actually utilizing our resources. Okay, I mean, you can plan those resources according to these according to the Gantt chart that you prepared, right? So it is easier to identify parallel activities in a project using a PERT chart. So by using PERT chart also, you will be able to, through PERT chart, what you can identify there what are the parallel activities and what are the, those things can be easily visible, right? So now project manager designates certain key events such as completion of some important activity as a milestone, right? So, usually you see by, your project manager always says that, okay, so these are the activities should be finished by this month end. Okay, so this way so your project manager will have certain, certain key events. Okay, events maybe, maybe they wanted to say that we need to give a demonstration of whatever the activities that we have done. Okay, so whatever the activities we have carried so far, right? So this way. So a milestone can be the preparation and review of the SRS document, right? You understand what is a milestone, okay? So this is exactly preparation and review of anything. So so one example of a milestone can be the SRS, okay? So once the SRS document is prepared, okay, and then you need to, I think we should, review that particular, SRS. So that is what exactly a milestone. Okay, once after it is reviewed by the developer, by the management, and by the customers, then only we can say that SRS part is, we reached that particular milestone. Okay, so once milestone is reached, the project manager can assume some measurable progress has been made. That is what. Okay, so once if you reach that particular milestone, then you can say that yes, so we have made some progress so far, right? So this Gantt chart will be used to, yeah, this is used to help the project manager, you know, in a way of measuring the progress, right? So is it fine? So any doubts so far?
No, sir.
Okay. Now let me change the other slide. Right. So now we'll see the new topic. It's a software design. So we have seen so far project estimations, project planning, project management. We have seen, right? And prior to that, we have seen the SRS part. Okay. So that means the requirement analysis part is done, and then now we are into software design part. Okay. So mostly, so hereafter we'll talk about function oriented software design, and thereafter we'll talk about object oriented software design. So these are the two traditional approaches we have, not traditional, these are the two approaches today we have. Okay, so we'll discuss these are the two software design approaches. Okay, and thereafter we'll be getting into uh, coding part, but usually as part of coding, there are very basic topics, so we'll not have many much topics, but and thereafter we'll be getting into the testing. Usually we are going through a flow, right? Probably you understand through my all lectures. So I have a flow. Okay, I maintain a very flow, like it started with problem, definitions, and then we have started with requirement analysis, right? And then we have gone into the feasibility study, and then we have seen part of a little bit like project management, and then we are now into software design, right? So as part of this lecture, we will see goodness of a design, like you are going to have these designs, but you should be able to assess that how good your design is, right? And we'll see here there are functional independence, and there is a cohesion, coupling. Okay, and then we will compare function oriented design with the object oriented design, right? Now, so when I say design, so usually as part of design, what exactly it does? So usually your design phase involves like so it is going to transform the SRS document, okay, into a form which can be easily implemented, using some programming language. This is what exactly we try to do, right? So ultimately, by taking this SRS document and after carrying out certain design activities, now ultimately what we are going to see, we will be going to see a design document. Okay, certain items were designed during the design phase. What the first is module structure, right? So as part of module structure, what you see, so first initially you try to identify what are the different modules. I think we have a little bit talked about the design when we are talking about different phases of the life cycle models, right? Already we have talked about them. Okay, so again I am repeating certain things, but we will be talking a little more interesting topics under this. So I just quickly go through these all topics, which already we have discussed indirectly or directly in the other topic, right? When we were talking about different phases, right? There we have talked about the design phase, right? So I already talked about something called structure chart. You have seen, right? And then we have seen software architecture, right? So there, those things all part of design only, right? So here, during design phase, so one is that we try to, look into the module structure of the project. Okay, so where we try to identify different modules, and then, then we try to see what different collection of functions and data being shared by these all functions is part of a particular module. Okay. So there will be a module. When we say module, so that module may contain certain number of functions, and these functions may be sharing some data. Okay, so each module accomplishes some well-defined task. Okay, so usually you have a goal for that particular module, right? So each module should be named according to the task it performs, right? Usually the module name, so you usually give a name, right? So like requirement analysis, I say. So maybe if you see the whole software engineering process as a project, now so requirement analysis can be one of the module, you can say. Okay, or you can talk about, like we have seen management information system example. There also we have seen certain number of modules, right? So then we have a control relationship among these modules, right? So now, as I told you, so there are certain modules, and these modules, right? Um, so there are so part of these modules, so you have certain number of functions, and then some of functions of maybe one function, maybe a function from one module is going to call to the function of other module. So that is what possible also, right? So in case of Java, so Java programming, you see there is a concept of RMI. There is a concept of RMI, remote method invocation, right? So you can see there is a local function calling, and there is a um, function calling over the network, right? So that is what exactly a RMI, right? So these sort of things, so these relationships exist among the modules should be identified. So you need to try to find out what relationships these all different modules they have. Okay, so which module is going to call which other module, right? So that is what the relation, there is a control relationship, right? So interface among different modules. Okay, so what sort of data are being exactly exchanged among these different modules? So that is what we call as interface, right? So you need to identify the interfaces among these modules also, right? So those things will be carried out as part of design. So data structures of individual modules. Okay, what sort of suitable data structures are really required? How you can manage the data of a particular module? So those things will be designed as part of the design phase, right? We have seen, right? So now, and also we'll be defining what are the suitable algorithms for each and every module. Okay, so because each and every module, going through certain number of processings, right? So that means you need to have some sort of algorithms for those processings, right? So those things will be designed as part of each and every, as part of this design phase. And so along with these design activities, so you should also be documenting them, okay, at the same time. So now, we can classify these design activities like a good software design, bad software design, right? So why you do these things? Because always you need to know certainly some of the bad characteristics of a good design. Then only you will be able to come up with a good software design. Otherwise, it will be very difficult, right? So often we arrive through a single step procedure, right? Rather, it requires iterating over a series of steps called design activities, right? So what we try to do is, so mostly whenever you are going through any design, so you should not be going through many iterations, right? So that means you redesigning. So mostly we going through certain iterations, right? So as to come up with the accurate design, okay, or the the efficient design that you can come up with, right? So but it would be good that if you can come up with a good design, okay, in a single step design, right? So these design activities are usually classified in two stages, right? So something called as high level design, that is a preliminary, or the detailed design. You can understand now. So as part of each and every activity, you can say they can be following into these two stages. Okay. So one is we have already discussed about this, like high level design as well as detailed design, right? So again we are reiterating them, okay. I reiterating those things, right? So now you can see meaning and scope of the two stages, right? So they vary considerably from one method to the other, okay. So as part of any high level design, what we are trying to do, so you try to whatever the high level problem that you have, that will be decomposed into certain number of modules, okay. And then you try to identify what relationships that exist among these modules. So you try to identify them, right, as well as interfaces. That is what I already explained to you, right? So those things will be carried out as part of any function oriented design, okay. But if it is a object oriented design, so it will be little different, but we'll understand later on, okay. As of now, so for any traditional function oriented design, so usually, so as part of function oriented design approach, usually you will have all functions, okay, right? Where in case of object oriented, so we'll talk about objects, right? So there is a difference, right? So the outcome of high level design is a software architecture. Now we have seen this software architecture in the very we have discussed about that, right? So now, we have several notations to represent this high level design. We have already discussed about this structure chart in our when we are talking about this design phase, during the very initial lectures, right? So I have told you, so it follows some sort of tree structure, tree-like diagram, right? So very high level module will be kept at the root level, and now the leaf level are the ones which can be directly implemented using some sort of algorithms or data structures, right? So as part of your function oriented, so you will have a structure chart sort of representations to come up with your software architecture, right? So now in case of object oriented design, we will talk about some UML diagrams. Okay, they are the ones going to represent your high level design. Okay, as part of object oriented design, we will talk about separately UML diagrams when you are talking about this object oriented design. Okay, so apart from this structure chart and the object oriented design, so there are some other notations people have used, right? So like Jackson diagram, Warnier rod diagram. So you can further read if you want to know more about them. But certainly we will not be talking much about this, but we will talk about structure chart. And this already we have talked about structure chart, right? We have seen, and now maybe in the next to next lecture we'll be talking about these UML diagrams. Okay. So now as part of detailed design, so for each module you try to identify what sort of data structure you really require for each and every module. Okay, what is the algorithm, efficient algorithm that you require as part of a module. So that is what examined. Outcome of detailed design is the module specification. Okay, so after this you will be going to get I mean the specification for each and every module. That is what the output from a detailed design you have seen, right? So that means what functions, what operations it has, right? So those sort of thing, right? So now so we'll be into good and bad designs also. We can classify. This is what I told you very beginning, right? So first thing that you need to know whether it's a good design or it's a bad design. So unless or until you know certain bad attributes, so you may not be able to come up with a very good design. So what is a good software design? So it should implement all functionalities of the system correctly, right? So whatever the functionalities that are being identified as part of SRS, so you are whatever the design that you are coming up with, so that should address all of the functionalities. Okay, so they should be they should be correctly implemented. Okay, right? So this should be easily understandable. Okay, so whatever the design that you come up with, so that should be very easy to understand. Okay, if something is not easy to understand, then probably maybe there will be some sort of ambiguity. Okay, so as a result, so the design may not be good. Okay, so should be efficient. Okay, it should be very efficient in the terms that means, so the design whatever you come up with, okay, that should address whether in terms of resources, whether we are optimizing or not, whether in terms of time we are optimizing or not, whether in terms of cost we are optimizing or not. Okay, so that should address this. Okay, so there should be optimization of these things: resource, time, cost. Okay, so if you are coming up with a design now which will take more time, more cost, more resources, then probably we will not say that that particular design is a good design. So good design always address resource optimization, okay, as well as time cost. So should be easily amenable to change, right? So that means the software, good software design should be maintainable, right? It should be maintainable. That means, so whatever the design that you have today, it should be very adaptable for us to make changes in the design. Okay, so if whatever the design you come up with today, so if that doesn't allow you to make changes at later point of time, then probably it is not a good design. So the other one is the understandability of a design. That is what I discussed, right? So it determines goodness of a design. It design that it is easy to understand. Also, it is easy to maintain and change. Okay, if something is very easy to understand, then only we can maintain it, as well as you can make certain changes to the design, right? So if it is not easy to understand, then there will be a that means that is very too complex to understand, right? So unless a design is easy to understand, so you require more effort to maintain that particular design when you require some maintenance. Okay, we already know that 60% of effort is spent in maintenance, because 60%, I mean, measure block of time is given to maintenance. So if your design is very complex during maintenance, so when you look into that particular design and it will be very difficult to understand, then probably you will not be able to maintain your software. That is what we say. Okay, if the software is not easy to understand, so then maintenance effort would increase by many folds. Okay, that is what we say. Understandability, you understand, right? So I mean, so it should use very consistent, meaningful names when you are going through, decompositions, right? Because you are going to decompose the, large module into smaller modules. That is what we call as modularity. So now these modules, different modules, they actually, arranged in a hierarchy. That is what we have seen in case of structure chart, right? So now it has the other characteristics of the software design, that modularity is a fundamental attribute of any good design, right? So because it helps us to understand the whole complex problem in a easier way, right? So because if you look at with a high level module, then probably you will not be able to understand, right? But if you divide these modules into some modules, probably you will be able to understand in a better way, right? If at all any complexities are hidden within that particular large module, that will be visible when you going into smaller modules, when you divide that into smaller modules, right? So your decomposition of a problem clearly into modules. So modules are almost independent of each other and divide and conquer principle. This is what exactly we say. So you try to do what? So large problem is divided into smaller problems, and then you giving optimum solution to each and every small problems, right? So once you got given the optimum solution to each and every problem, that means you have given optimum solution to the large problem, right? So this is what exactly one of the attribute of good design as well as modularity. Okay, these modules can be understood separately. That means that is what I say. So so remember that it is very difficult to break a bunch of sticks, but very easy to break the sticks individually. Okay, so now you understand with this proverb, probably we always use, right? So unity is the strength. Okay, so what will happen? But here it is something reverse. Okay, we see something like this. Okay, now what will happen? So if a group of sticks, it is very difficult for us to break, right? But if you take those sticks individually, then you can easily break that. Okay, that means, so here you can understand in a better way. Okay, because each and every stick individually. That is what we are trying to say. Now this is what exactly happens as part of a so decomposition of different modules, right? Now can you tell me, so according to you, which one is clearly decomposed, the left one or the right one?
Left one.
Sir, first
Left
one.
one, right? Left one or the right one?
Left one, sir.
So left one looks better, right? You can see, I mean, which module is decomposed into which other two modules, right? But here in this case, it is quite very difficult to understand the right one. Okay, so that means that the right one is not clearly decomposed. Okay, so the structure is not okay. So as part of modularity, so there are two topics we will see mostly. That is high, there is a cohesion and there is a coupling, right? So we need high cohesion. That means I mean, when you say cohesion, that means how what is independence each and every module has. Okay, degree of independence, that means how cohesively that module is, how cohesive that particular module is. Okay, and coupling is something, so how I mean coupling is going to give you the degree of interdependency. Okay, it is going to give you interdependency. That means how how much a particular module is dependent on the other modules. Okay, so that is what exactly a coupling. Okay, so cohesion is a independence. Okay, and coupling is interdependence. Okay, so as a result, you see, I told you before, right? So if the modules are very independent, then what will happen? You can easily maintain those modules, right? You can easily maintain those modules whenever you find any problem. But if those modules are dependent on any other module, then what will happen? If you are going to make changes to one module, then definitely you need to accordingly need to make changes in the other modules also, right? So that is the difficulty. That is the reason why. So you need to always have high cohesion, that is what really required, as well as you need to have very low coupling. Okay, so that means interdependency should be very low, and the module should be very much independent. Okay, so they should not dependent on any other one. Okay, so that is so these are the two metrics, so probably we'll see. So that is what we say cohesion and coupling, right? So usually as part of any degree you see fan out means the the errors going out from a particular module, right? So that should be very low. Okay, that should be very low. Okay, and so it should maintain the abstraction. Okay, so this is what exactly I said you. The cohesion is a measure of functional strength of a module. The cohesive module performs a single task or a function. That means it is a completely independent function. Okay, so it is not taking any help from any other function. Okay, so you can say in this way. Okay, and coupling between two modules is a measure of degree of interdependence or interaction between two modules. Okay, so how often a particular module is talking to other module. Okay, other modules. So that is what exactly a coupling we say. So now a module having high cohesion and low coupling, that is what I said you, right? So functionally, so something should be independent of other modules. Okay, and now these functionally independent modules has a minimal interaction, right? So someone is very much independent, right? So that means it is not going to take any help from any other module, right? That means mostly it is independent, right? So we try to do this way, we try to see this way, right? Now so what are the advantages of functional independence? So you can better understand each and every module. Okay, you can design the module in a better way, right? So the overall complexity of the design can be reduced. Okay, so that is what I said you. So I mean each and every module can be understood in a isolation. That means independently you can understand in a better way. Now functional independence reduces error propagation. That is what I said you, right? So if let's say you made some errors in one module, and if it is dependent on let's say there is a module A and there is a module B. Now B is dependent on A. Let's say if the error is introduced in module A, then what will happen? Because B is also dependent on A, so whatever the errors that are there in the module A, that will be also propagating to the other module. So now as a result, so and sometimes it is very difficult for us to debug where that particular error is. Okay, whether the error is in the module A or module B. So debugging also makes very much difficult, right? So there are these sort of errors, right? So degree of interaction between two modules is low. So that means that should be very low, then only it is good. And error existing in one module does not directly affect the other module if they are independent most of the time. Then so any error comes in any of the modules. So that is what so makes us very easy for to maintain the software. I told you very at the very beginning, right? If you find any bug in the module, so you can maintain that particular bug separately. I mean, you are not going to disturb any other module, right? So reuse of module is also possible, right? So that is also another advantages. So you can reuse whenever you have, okay, because they are all independent ones. A functional independent module, can be easily taken out and reused in a different program. That is what I said you. So each module does some well-defined and precise function. The interfaces of module with other module is simple and minimal because they are much more independent. So as a result, the interfaces may not be much complex, but if they are very much dependent, so then what will happen? The interface that you need to design between these modules must be a complex one, okay, because much of the data will be exchanged among these two modules. As a result, you need a complex interfaces, right? So functional independence, so unfortunately there are no ways to quantitatively measure the degree of cohesion and coupling, okay. So we'll try to see different categories, classifications of this coupling and cohesion further, okay. So first we'll talk about the classification of cohesiveness, and then we'll talk about the classification of the other ones, right? So we'll talk about how these cohesiveness, what are different types of cohesiveness, okay. So each and every module can display, right? We'll see those things, right? So now the cohesiveness is, now you have something like this. So these are the various classification of cohesiveness. So starting from coincidental to functional, so your degree of cohesion slowly introduced, okay. So you have a low degree of cohesion at the coincidental, okay, and you have slowly we are going towards higher cohesiveness when we have functional class of um, you know cohesion, okay. We'll see each and every one. What is a coincidental, right? So whenever you have a module that performs a set of tasks, usually you know that, right? So these modules, I mean these tasks actually they relate to each other very loosely, and they do not these part of a particular module. You have a very random collection of functions. Yeah. So I mean, you have not given well thought process uh, while you have designed all of these functions, right? So whatever the functions you have you thought of, like what, so coincidentally you will be going to get some sort of functions, right? And you have developed some of these functions, and then you will be putting all of these random functions, okay, part of a particular module, right? So usually you will have a very low cohesion, okay. You will have very low cohesion, right? That means so you cannot maintain that independence, okay. So because cohesion will be very low here, okay. So because they are all random functions, right? So you do not know, I mean, which one will be dependent, which will not be independent. You do not know nothing, you do not know nothing about this, right? So you will get very certainly very little less cohesiveness. But if it is a logical cohesion, so as part of a particular module, so whatever the functions or the elements that you have, so they will always they perform some similar operations, okay. They will perform some similar operations. Let's say for example, so you have certain number of printing functions, okay. So the printing functions is going to print some reports from some specific tasks, okay, part of this in a module, okay. So if there are three different tasks there, for each of the tasks you are going to your print function is going to print what? The report, right? Now this printing function has similar operations. Okay, I mean it can handle the error if at all it has. It always take the data input. It is giving some data output, right? So this printing function will have similar operations. Okay, so you have set of functions, and these all set of functions will have similar sort of operation as part of those functions. Then we can say they are logically cohesive. Okay, that means logical cohesion. Okay, do you understand? Any doubts so far? Now, what is a temporal cohesion? So the module contains tasks that are related by the fact that all the tasks must be executed in the same time span. Okay. So now, so you can see there are some functions. Okay. So, maybe you can see as part of a particular module, you have 10 functions, and these all 10 functions required to be executed, at the same time. Okay, or during a particular time span, these all of the functions should be executed. Then we can say they are temporally cohesive. Okay, these functions of a module are temporally cohesive. Like one example of a as part of a operating system, right? You can see. So whenever you start your machine, so what will happen? Sometimes the initialization, startup, shutdown of some processes. So usually, or you can see when you are going to close your machine, so initially what happens? So your operating system carry out some of these operations at the same time. Okay, so that means initialization will be done, and then you loading the memory locations, or so many things, or some of these processes will be shut down. Okay, so those things will be carried out at the same time. Okay, so then though that particular module is called as temporal, has a property of temporal cohesion. Okay, now there is a procedural cohesion, I said you. So the set of functions of the module, all parts of the procedures or certain sequences of steps has to be carried out in a certain order for achieving an objective. Right, now what will happen? So here, so as part of a procedural cohesion, what will happen? So there are certain number of functions of a module, and these functions will be executed one after the other. Okay, but the data they will be using, okay, that the functions, the whatever they will be working on a set of on any particular data will be different. Okay, I mean on different sets of data, so these functions will be working, right? That means you have some functions, okay, and these functions are actually completely you can see they are carrying out different activities. Okay, they are carrying out different activities. Okay, but now these activities will be carried out, but these activities will be carried out one after the other. Okay, so you can think of like algorithm for decoding a message. Okay, so you can see, okay, so steps as part of decoding a message, right? Or encoding or decoding, you understand, right? So maybe you can think of that means first you will be doing something, thereafter you will be doing something, and thereafter you will be doing something, right? So this way. So communicational cohesion, the other one is a communicational. So here all function of the module, so they use same data structure. Okay, if when can you say a particular module has a communicational cohesion? When all of the functions will use the same data structure. Okay, so they will be operated on the same data structure, then you will say communicational, because you see, so they will be these functions are communicating through a data structure. That is what, okay, so they are all communicating to each other through a particular data structure. That is what actually the mean. Okay, so that means they are going to use the same data structure, and they are going to update the same data structure. All of these functions going to operate on the same data structure. Then we can say that's a example of a communicational cohesion. Now, what is a sequential cohesion? So here now it is something like this. Okay, so you have some of these functions, right? Unless the sort function is completed fast, so you cannot go into the sets. Okay, now here what is happening? So the output of sort function is given as a input to the search function. Now output of search function is given as a input to the display. Now here this way, whenever you see this way, so now then it is called a sequential cohesion. Okay, clear? But in case of procedural cohesion, there also I told you, right? So there also you carry out sequentially one after the other activity, but the data, they are taking as a input, or they are giving the output. So they are, those functions actually, operate on different data. Okay, that means they are carrying out different sort of activities. Okay, they are completely independent from each other. Still, you need to carry out the activities in order. Like you can think of, right? Whenever you wanted to place an order in your Amazon account, so what you need to do first? First, you need to log in. Okay, first you need to log in into the account. Then only you are allowed to search an element, okay, or item. Okay, and then you need to place those items in a bucket, right? And before you leave the account, maybe once if you place that, so before you through to a payment, right? Now there are certain activities need to be carried out, one after the other, but those functions are operating on a different data set. Okay, I mean different data, right? So but here if you find sequential cohesion, in this case what will happen now? So the output of sort function will be given as a input to the search function. Okay, now output of the search function will be given as a input. If this sort of functions that you will find, then that particular module has the sequential cohesion. Okay, now the last one is a functional cohesion. So here what will happen? So you can think of something like this: different elements of a module cooperate to achieve a single function. Okay, so now when the functional cohesion actually depicts that you have certain number of functions, right? So these functions actually cooperate among themselves so as to execute a particular behavior or a particular function. Okay, so when you see these sort of things, so then we can say that it's a functional cohesion. Okay, so we'll continue in the next lecture from hereafter. Okay, so I just download the attendance. Like any doubts of our students?
No, sir.
Okay, so then I should terminate the lecture. Okay, I leave the lecture and tomorrow we'll meet again. Huh? Okay.